Prof, can you hear me now?
Yes, thank you very much. Please go ahead.
Thank you so much. Thank you. I think my mic was muted. So thank you so much for allowing me to join this conference. Today I want to talk about probing the charge transfer, generation rate, transfer collection in organic solar cells. And I want to compare fullerene and non-fullerene acceptors. So I'll explain what they mean. And yes, so my talk will be so first I want to introduce renewable energy. I know it has been done here before. And then we introduce what we are doing to, in our labs, which are organic solar cells to be precise. Then we shall look at the optical characterization that we have, the morphology of these devices and films. And then we look at the charge generation, separation, and collection. And then we conclude. So ideally, this is a common phenomenon. Maybe if I can use a pointer. So this is a common phenomenon that we have with increasing population and the demand for energy going up. And you look at it in terms of what is causing this kind of pollution, and you find that 25% majorly comes from electricity and heat generation. So as we look for sources of energy, generate electricity, we end up with this kind of scenario in our environment. And therefore, we need to have more concentration on a better way to generate our electricity and heat without polluting the environment. And one of the ways that we suggest is the use of solar. And if you look at it in terms of what we have, if you look at this amount of energy that is reaching us from the sun and versus what we the global energy demand or what we can consume globally, then we realize that we only need 0.01% of this to satisfy our demand. If you look at it down to the number of panels that we can put on our houses or rooftops, then look at the surface area that will be covered, then we are talking about this as small as this dot globally to satisfy what our demand is. Bring a case of South Africa, for instance, where you have a population of about 61 million. We only need 2.6 times 10 to the power 11 watts of energy, which is a very small percentage of what we have. So what are the strategies that are there? Of course, solar cell is not a new thing. It started with Edmund Becquerel in 1939. Then, of course, comes the first generations of the solar cell, the second generations. And what we are currently looking at are third generation, of course, with the high prospects of the fourth generation, where you look at what you call the hybrid solar cells. So in our labs, we are looking at the nanocrystals, the polymer-based solar cells, the dye-sensitized solar cells, and of course, the hot debate now, which is the perovskites. Of course, they also have their challenges, but they give us a very good prospects for the future source of energy. So why are we looking at these organic solar cells to be sized? So we look at organic solar cells in terms of the cost. The cost is relatively projected to be cheaper than what we have as silicon, because then also in terms of flexibility, you can print this on a flexible substrate. And of course, they also have their response to optoelectronic response, of course, is very high. And then you can also tune the bandgap. That means that you can determine which part of the solar spectrum you want to absorb, and you can stretch it to have maximum absorption as you want. And that comes with attunable bandgap, which of course silicon will not give you. But of course, we have the limitations such as low efficiencies, which is between 10 to 12. Of course, some have stretches to 20, but again, Even if you stretch the efficiency, we still have a problem with stability. They are not stable when they're exposed to moisture, where you want these panels also to be erected on rooftop where you have them exposed to air. And if they suffer this problem of stability, then of course that limits their performance in the open air. So what we are doing is we're using a few strategies. One of them is the use of nanoparticles, which we propose we call plasmons. And this is able to couple with the incoming light and trap the light and increase the absorption within the solar cell. We also have interpenetrated network. I'm going to just explain it in a short while. And then we have the energetics and kinetics. So that's the use of probably heating or changing of the energy, the energy of these molecules to make them absorb have optimum absorption. Then, of course, we also have the spectral conversion, which means that you want to regulate which part of the solar spectrum you are able to absorb. That can be done through either a down conversion or an up conversion, where you have the energy coming from the sun is either split to what the solar cell can absorb, or you have two photons which are matched together to have what the solar cells can absorb depending on their band gaps. So ideally, if you look at what we call organic solar cells, these materials, their difference with the silicon is that they have a low dielectric constant. So that means that when light falls on them, we will not be able to get free charge carriers at once. So what will happen is that you get a hole and electron which are canonically bound, which are called excitons. And therefore, you need two materials such that at the boundary of these two materials, you have an energy difference which will be used to separate these charge carriers into free electrons and holes. So if you look at here, incoming light generates an exciton hole pair, and this electron hole pair has to diffuse to the boundary where the separation is taking place. And this diffusion length is normally very small, between 10 to 20 nanometers. This therefore limits the thickness of the solar, what we call the active layer that you should have, because if you have a bigger active layer, yes, you'll be able to absorb more light, but you lose them because the excitons have got a very short diffusion length, and therefore they'll not be able to reach their boundary. So it means that you have to optimize between thickness and the diffusion length that you have. So once they reach here at the boundary, of course, the energy difference enable them to be separated into free charge carriers. And then you can collect the different charge carriers at different electrodes, where one is collected at the cathode and another one collected. And therefore, it means that what we need to work around is creating a donor and acceptor materials that are very close to each other. And this is normally the ideal structure that you want. But in our case, we use a mixing where you have a solution. So these things are powders. They are dissolved in different solvents. Mostly we use chlorobenzene. And therefore, you make the acceptor and the donor materials very close to each other. In such a case, the physics part of it is that we want to look at the absorption, and the transport, and the recombination. Of course, if you look at a solar cell in terms of a diode characteristics, then you'll want to see a curve that looks like this. And the absorption will affect how much current you are collecting. So in terms of the current density, while transport system will be looked at in terms of a mobility system, which of course affect the quality of this device, which is normally noted as a fill factor. And you also have the recombination, which is dictated by the lifetime, how long this excitons takes before they recombine. So our research goes around trying to optimize, and this is done either through simulations or experimentally, to see how to optimize all this, the absorption coefficient, the mobility lifetime, and the mobility and lifetime in order to get an optimum device. So ideally, I choose to look at a device where you have a definite donor material, and then I will look at two acceptor materials where one is classified as a fullerene acceptor, another one is classified as a non-fullerene acceptor. So we want to look at a case whereby you have a donor material which is blended with just one fullerene acceptor, and we shall call it a binary system. And then we can have a case where you have a donor material which is, of course, mixed with both fullerene and non-fullerene, and we'll call it the ternary system. And we want to see what is the device performance within, whether comparing the binary and the ternary system in this case. Of course, these materials that are being chosen must have an energy gaps, which are energy levels which are cascading, so that the charge carriers can move freely from where they are created to the electrodes without much traps. So if you look at it, the easiest way or the quickest way is to look at how much absorption is we have within the device, and see if do we look at absorption as the ultimate determinant of the performance of the device. So the first thing is to look at the absorption profile. And if you look at here, you're seeing that they have a binary case where you just have a donor material and an acceptor material, which in this case, I'm using a fullerene material, and the absorption is quite high compared to other ternary system where you have a 3 that is a donor and 2 acceptor materials. So we wanted to probe, if you have high absorption, does it translate to high efficiency? So the next thing is to look at how much capability of having this charge separation at the boundary. And this, the easiest way to look at it is look at the PL quenching. So you look at the photoluminescence of these materials, the pristine one. So you can see that the pristine one, starting from the red and this and the blue one, of course, and the donor material, compared to when you have a blend. Of course, there will be a photoluminescence quenching, and that gives you a clue that, of course, there is charge separation taking place. And we wanted to see if this PL quenching changes within the ternary blend. So for instance, as you increase the fullerene material or increase the non-fullerene acceptor material, do you have a difference in PL quenching? And we ended up not having any difference, because the energy difference between these acceptor materials are very close, and therefore you're not expecting an energy transfer or a charge transfer between an acceptor and an acceptor. So it means that what we are having is just an energy transfer between a donor material and an acceptor material, which is either a fullerene or a non-fullerene material. Then we went further and look at now the morphology of this. So we look at these materials in terms of the structure, and this can be seen from microscopic perspective to nanomorphology aspect. So from microscopic, we can look at this from atomic force microscopy. And of course, you'll be able to see the weighting of layers, the transport paths, the domain size, and the composition of these domains within the material. And then, of course, we can also look at it in terms of the nanomorphology, where you can see the purity and determine how crystalline these materials are and how they're oriented onto this on the surface where they are being deposited. So microscopically, we did an AFM, and you look at this material, of them. And of course, we want a material where the surface is smoother. So the smoother the surface means that you're going to have less traps where you're going to lose these charge carriers. And we got this from the 2-1-1 combination, where the acceptor and the donor material, I mean, the two acceptors have the same ratio were blended with a donor material. Then, of course, if you want to look at how these molecules are oriented on the surface, then you want to look at the side chains. The side chains are oriented to each other. In a case where you have the side chains in one direction, then you have what you call a head-to-head orientation. But if you have them facing opposite direction, then you have what you call a head-to-head orientation. So this head-tail or a head-to-head orientation gives you how regular these molecules are. And of course, we can quantify them using a photoluminescence studies. So if you look at the first, of course, in photoluminescence, you have two peaks. So if you look at the first vibromic peaks and the second vibromic peaks, the ratio will give you what is, which orientation is dominant. So you can have this, if you have, let's say, head to tail, then you can classify it as a J aggregate. And if you have head to head or a tail to tail, we can classify it as a H aggregate. And the proportion of how much we have can be obtained using the ratio. So if you have a low ratio of this first peak to the second peak, then it means that you have a J orientation or J aggregate where the molecules are facing one direction, and therefore these materials are seen to be much regular or crystalline, and the flow of the charge carriers is easier compared to the other part. So the other bit is to look at it in terms of the devices that we made, and we find that you're starting from the binary device to the ternary device, and you find that the 2-to-1, 2-1-1, and 3-1-1 have the lowest ratio. And of course, we are comparing this with the full width half maximum, which is normally the determinant or the easiest way to look at the crystallinity of these materials. And you see that they are talking to each other, that the lower the ratio, the lower the width, and therefore we're having materials which are a crystalline system where the charge transfer or the charge transport is much easier. Then, of course, we can also look at the Gmax, that is grazing incidence, wide angle scattering. And this is where you have an incident ray at a small, of course, small angle, theta. And then you have a 2D detector where you have either the in-plane and out-of-plane scattering. And then, of course, if you stretch, depending on how far the detector is, you can have a Gmax, that is a grazing incidence wide angle scattering, or a Gsax, which is a grazing incidence small angle scattering. And of course, this will give us the orientation, how these molecules are oriented on the surface, which can either be a face on or an edge on. And of course, this determines how free the charge carriers are able to move from where they are formed to the electrons. So we looked at this in two ways. One, we look at the power law, that is to look at how much the biomolecular recombination that we have, of course, and then we look at the ratios, the different ratios, and see what is the ratio or what is the dominant recombination that we have there. And we can also look at this also in terms of the what we call the VOC versus the lean or the light intensity. And that will give us whether you have a trap assisted or a more bimolecular recombination taking place. And of course, the ratios here is, so if we have a high gradient, then it means that you have a more trap assisted recombination, and that is what we are seeing here. Then we compare this with the conventional way of looking at the performance of the device, looking at the open circuit voltage, the current density, and the fill factor. And then we derive what is the device performance depending on this power law and the VOC versus the power intensity. Then, of course, one thing that we can also generate is we can measure the devices both in darkness or in when exposed to light. When you get the current density difference between the two, then you get what we call a photocurrent density. And if you plot this against the effective voltage, then you can get what we call a saturation current, which is shown here. And the saturation current is an indication of how the charge carrier transmission and collections capability within the device. So you see that the 2-to-1-1 device shows a very high saturation current density, which is an indication of a better charge carrier transmission within the device. Then we also have another aspect which you can use to characterize this device is once you got the saturation current, then you can plot that against the effective voltage to get how easy was it to separate these charges. Of course, this will speak to the photoluminescence data that we have when we're looking at the PL quenching that we have. And again, we conclude that the 2-to-1-men device gives us a better charge separation capability within the device. So this is just one aspect of looking at the device performance when you look at the light capability of absorbing light and other factors like the light, the charge separation, the transport within the device. And we conclude that even if you can have a high absorption profile, we need to look at how these charge carriers can be easily separated, how they can be transported to the electrodes. And this is what we have found in this study. So of course, the summary gives us the convectional performance of these devices versus what the maximum generated current, and of course the charge dissociation and the collection capability that we have just seen here. And this is subject to, so it therefore means that apart from just having high absorption, we need to look at the charge separation, we need to look at the charge transport to the electrodes, which will be very good indicators for these devices. And of course, this gave us a better performance among the devices. So this is just a small part of what we are doing, and I would like to thank the ARUA for their support that came at the right time when we wanted to analyze our data at WITS, and of course the host WITS for this. And these experiments were done at Oxford, so we thank them so much for this support and the opportunity. And I thank you all for listening to me. Thank you. Prof, can you still hear me?
Yes, I can. Thank you very much, Francis, for a very nice talk.